Good morning, students. Chapter 4, Moving Charges and Magnetism. Yes, in one lecture we have obtained one equation of torque acting on rectangular current carrying coil in uniform magnetic field. If you know that case. Okay, what is torque? What is torque? See, torque acting on current carrying loop in magnetic field. It is given by tau is equal to m cross b, or I can write its magnitude. Tau is equal to mb sin theta, or I can write tau is equal to m magnetic moment means m I a b sin theta. Clear about this? So yes, this case you already know. This case you already know. Okay, moving coil galvanometer. Galvanometer is a device which is used to measure volt and current, voltage and current. Yes, Ohm's law. What is experiment of Ohm's law? Yes, you have to consider one resistance. Find what is potential difference between two ends of resistance and find what is current flowing from resistance. So obviously, to measure current, you have to use ammeter. To measure volt potential difference, you have to consider voltmeter. Then yes, voltmeter and ammeter, how voltmeter and ammeter they are formed. What is used to measure current and voltage? To measure current and voltage, we have to use moving coil galvanometer. So why they are used? Moving coil galvanometer. Moving coil galvanometer meters are used to measure current and voltage across given loop. Clear about this? So first of all, what is this? It is its principle. In this box, torque acting on current carrying loop in magnetic field, tau is equal to m cross b. It is an it is its principle. Okay, what is its principle? When current carrying loop is placed in magnetic field, it rotates. So yes, we know that when current loop is placed in magnetic field, due to torque acting, it rotates. Clear about this? So yes, it is its principle. Now what is its construction? See, two magnetic poles like this. They are used. Like it is north pole and it is south pole. Clear about this? Okay. Between these two magnetic poles, here one cylindrical core of soft iron, made up of soft iron, is placed. It is top view actually. It is top view. On this soft iron, at this point, at this center, one current carrying coil having angles. Is pivoted. Clear about this? Okay. Now see, here it is. These two magnetic poles are there. Why this soft iron core is used? To maintain uniform radial magnetic field. Why they are in this shape? To produce radial magnetic field. To produce radial magnetic field like this. To produce radial magnetic field. To produce radial magnetic field. Uniform radial magnetic field. Uniform radial magnetic field. Uniform radial magnetic field. Clear about this? Clear about this? So yes, it is uniform radial magnetic field. Uniform radial magnetic field. Clear about this? Yes, it is current carrying load. It is current carrying coil. Current carrying coil. Clear about this? Now it is pivoted at this point, and yes, it is attached with a spring. It is attached with a spring. It is attached with a spring. So yes, this coil is attached with a spring. This coil is attached with a spring. Clear about this? Okay. Now with this coil, one pointer is connected. One pointer is connected. It is pointer. It is pointer. Okay. And yes, this pointer, see, due to this magnetic field, it is current carrying in the coil. When current is flowing in coil, due to magnetic field, it performs rotational motion. So yes, as this coil performs rotational motion, this pointer also moves. This pointer also moves, and this pointer moves on circular scale like this. On circular scale like this. On circular scale like this. Clear about this? This pointer moves on the circular scale. It is scale. It is scale. Yes, here it is 0. And then on one side there are terminations. There are terminations. Clear about this? So yes, it is construction of moving coil galvanometer. Again, what is construction? Magnetic poles. Soft iron core. It is soft iron core. On this soft iron core, this coil is pivoted along with a spring connected with it. Okay. So yes, what is purpose of this soft iron core? To produce uniform radial magnetic field. Clear about this? This coil is placed like this with spring. Okay. Pointer is connected. It is circular scale. It is circular scale. Clear about this construction? Clear about this construction? Okay. Now see, here it is. See, here it is. When current is flowing from coil. This coil is placed in uniform magnetic field when current is flowing from coil. Torque acting on coil. Tau is equal to, yes, what is equation? Here it is. N I A B sine, here it is. C, here it is. It is torque. Okay, magnetic field is in radial direction. This loop, current carrying loop is placed like this. So what is its area vector? Its area vector is always perpendicular outside. And see, this loop will rotate in this direction like this. So its area vector, it is always perpendicular. It is always perpendicular to magnetic field. So remember, in moving coil galvanometer, area vector and magnetic field, they are always perpendicular. So here it is sine 90. Here it is sine 90. Clear about this? So when current is flowing from coil, torque acting on coil, tau is equal to NIAB sine 90, and yes, tau is equal to, it is NIAB, and due to this torque, this coil rotates. Due to torque NIAB, coil rotates. Now coil rotates. This coil is connected with spring. So yes, spring, elastic object, restoring torque is acting. Yes, you know concept of restoring force. If we have one spring, we compress that spring by giving some external force. See, it It is linear motion. Yes or no? So, for linear motion, which one is responsible? Force. So, when you compress by giving external force, restoring force is produced in opposite direction. Restoring force is producing opposite direction, and its equation is F is equal to Kx. F is equal to Kx. K, torsional constant of spring, and X is displacement. X is displacement. Here, this coil is performing rotational motion. Which one is responsible for rotational motion? Torque. So yes, as this coil is connected with spring, and as this coil rotates, that spring tries to regain its original position back. Means restoring torque is acting on coil. So see, due to spring, restoring torque is produced. Restoring torque is produced. Clear about this? Okay, restoring torque is produced. See, if it is coil, due to torque, tau is equal to NIAD, it is rotating in this direction, then restoring torque, it will act in opposite direction. Restoring torque, it will act in opposite direction. Clear about this? Okay, so yes, due to spring, restoring torque is produced. What is restoring torque? Restoring torque is equal to, it is K phi. Restoring torque is equal to, it is K phi. Remember, restoring force F is equal to Kx, x linear displacement. Restoring torque, tau is equal to K phi, angular displacement. Okay, if you want to come back. Okay, so restoring torque is equal to K phi, where what is K? K is torsional constant of spring, or it is also called K is restoring torque per unit twist. Twist means, see, as this coil rotates, spring is connected with it. So yes, that spring, in that spring, twist is produced. Clear? 1 twist, 2, 3, 4. So yes, this K is restoring torque per unit twist. Clear about this? Now what happens? Tau is equal to NIB, tries to rotate it. K phi, that is restoring torque, it tries to gain its original position back. So according to value of current, that coil will be in equilibrium condition when, or at position when they two will be having equal magnitude. Okay, so yes, when or at equilibrium means these two torques, they are acting in opposite direction. Okay, and if their magnitudes are equal, equilibrium means resultant torque is 0. So at equilibrium I can write NIKB is equal to, here it is at K phi. Now make phi a subject, then phi is equal to, it is NIKB upon K, or I can write phi is equal to, it is NKB upon K, and here it is I. I can write this term in bracket. Now see, N, numbers of turns for this given coil. For given coil, numbers of turns fixed. A, area of coil, fixed. B, magnetic field, fixed. K, torsional constant for spring, fixed. Yes or no? Then this phi means deflection. Phi means deflection. See, this pointer is moving. Means deflection. This pointer is moving means deflection. Clear about this? So see, this deflection depends on current. Okay, if more current is flowing, then deflection is more. Yes or no? Yes. If you have observed ammeter or voltmeter, okay, how you can say the current flowing is small or current flowing is more? Yes, here it is 0 point. If pointer is here, then yes, you will obviously say that current flowing is less. At this point, current flowing is more. So see, this current depends on this deflection. Sorry, deflection depends on this current. And yes, you have to remember this equation. You have to remember this equation. Deflection, phi is equal to NAB upon K into I. NAB upon K into I. Okay, so what happens? If it is one wire, current is flowing, it is galvanometer. It is galvanometer. Some current is flowing from this galvanometer. Clear about this? Then, according to that current, torque is equal to NIEP is acting on it. Restoring force is also acting on it. And coil will be in equilibrium when these two torques, they will be of equal magnitude. Coil will be in some equilibrium position. Let's suppose coil is here at this position. Okay, then yes, we can easily find what is its deflection. Means we can easily find what is current. So it is construction of moving coil galvanometer and how galvanometer works. And how galvanometer works. Clear about this? Clear about this? So yes, moving coil galvanometer. Now, we will use this galvanometer to measure current and voltage. To measure current and voltage. Okay. To measure current, that galvanometer is converted in ammeter. To measure voltage, that galvanometer is converted in ammeter. So now in next lecture we will discuss about how to convert galvanometer in ammeter and how to convert galvanometer in voltmeter. What is difference between ammeter and voltmeter? Okay, so yes, in this chapter, in this lecture, we have discussed about moving coil galvanometer. Use, principle, construction, working and equation. Clear about this? Right now.